Today we've got a really interesting video. So it's my take on the generalization of the notion of a right angle, or what it means for two rays to be perpendicular, or in other words, what it means for two vectors to be orthogonal. So often in the language of an abstract vector space, we would use the notion of orthogonal, but as we'll see today, that's just a generalization of what you learned about perpendicular lines in elementary algebra, in elementary geometry, I should say, or what it means to have a right angle in elementary geometry. The only thing that we'll assume here is the Pythagorean theorem, and then of course some stuff about vector spaces a bit later, but we've got a bit until we get there. So let's recall that the Pythagorean theorem is about triangles. So let's say we've got a triangle like this. So I'll draw it like this. And I'll put an angle here. Maybe I'll call this angle theta. And then maybe I'll also label the sides of this triangle. Let's say this side length is capital A, this side length is capital B, and this side length is capital C. And then the Pythagorean theorem says that theta equals 90 degrees if and only if a squared plus b squared equals c squared. So the Pythagorean theorem is not often written as an if and only if statement, but it is an if and only if statement. And via this Pythagorean theorem, we can really define what it means for an angle to be 90 degrees. And that is if two sides of a triangle have their squares add up to the square of the third side of the triangle. Okay, so now let's maybe put this in the Cartesian coordinate plane and then see how we can develop the notion of two perpendicular or orthogonal vectors out of this. So I'll just kind of assume without loss of generality that this point right here is sitting at the origin. I can always translate this around if it's not sitting at the origin. And then I'll put this guy right here to have coordinate A, comma B. And then I'll put the coordinate right here, C, comma D, where those are both lowercase. Great. And now what we'll do is express this equation a squared plus b squared equals c squared in terms of the distance formula for the distance from the origin to a comma b, the distance from the origin to c comma d, and then the distance between a comma b and c comma d. So let's see that. So let's notice that a squared plus b squared equals c squared if and only if, well, so the distance from the origin to a comma b is equal to a squared plus b squared. So that's pretty easy to check just with the distance formula. We won't do that super carefully. And then the distance from the origin to c comma d is likewise c squared plus d squared. And then the distance between these two, again, by the distance formula, is a minus c squared plus b minus d squared. Great. So those are the distances squared. So notice if we just wanted the distance, we would have a square root around all of those. But since we want the distances squared, because that's in the Pythagorean theorem, the square root disappears. Okay, so now let's multiply out this right-hand side just by foiling out these two binomials. This gives us a squared plus c squared minus 2ac. This gives us b squared plus d squared minus 2bd. And from here, we can do an obvious cancellation. So notice this a squared term will cancel this a squared term. This b squared term will cancel this b squared term. This c squared term cancels this c squared term. And then finally, this d squared term cancels this d squared term. And then we can rewrite this as the following statement. We have 2 times AC plus BD equals 0. So I guess we're going to assume that we're in the real numbers here, which means that 2 is not equal to 0. I think maybe it's interesting to think about what happens if we're in a field of characteristic 2, but we will not be in a field of characteristic 2. So what that tells us is that AC plus BD equals 0. But now that gives us some motivation for defining the dot product. Notice that is equivalent to AB, that vector, dot CD equals 0, where the dot product is defined just by this sum up here. So you multiply each of the kind of corresponding entries in the vector, and then you add them up. Okay. So that really brings us to the following definition. And so I'd like to point out that this definition kind of follows naturally from how we interpreted a right angle over here. And that would be like this. So two vectors, v and w in Rn. So we no longer really need to be in the plane. We can like slightly generalize this to Rn, are orthogonal. So we'll use the word orthogonal instead of perpendicular. So you can think about those as synonyms. So really we're just defining what it means for two vectors to be perpendicular. So they're orthogonal if and only if v dot w is equal to 0. So we'll take that as our definition. And then what's v dot w generally? Well, let's say v has entries v1 down to vn, and then w has vectors w1 down to wn. Then v dot w is equal to v1 w1 plus all the way up to vn wn. Great. So that's, like I said, our first crack at a generalization of what it means for two vectors to be perpendicular. Okay, so now that we've like motivated the definition of the dot product via these perpendicular lines over here, or this right angle, let's write down some common characteristics that the dot product satisfies. So far we started with what it means for an angle to be a right angle and built that up to the definition of orthogonal vectors within Rn via this thing called the dot product. Now that we've got this dot product, I'd like to present the following theorem. We will not prove this, although it's just simple arithmetic to prove it, about characteristics or properties that the dot product satisfies. So let's see what we have. So we need a triple of vectors in Rn. So we have u, v, w in Rn. And then we need two scalars, so a and b are in R. So we've got three vectors and two scalars, or two just numbers. And then the dot product satisfies the following three properties. So v dot v is always non-negative. So it's always bigger than or equal to 0 if you take the dot product of a vector with itself. And furthermore, the only way to get 0 is if you start with the 0 vector. So in other words, v dot v is 0 if and only if v is equal to 0. Okay, nice. And then next, there's some sort of symmetry or commutative property of the dot product. So v dot w is the same thing as w dot v. And then finally, there's some sort of distributive property of vector addition over the dot product and scalar multiplication interaction with the dot product as well. So that says that AU plus BV, let's recall that those are scalar multiples of U and V. So we've got AU plus BV dot W is the same thing as A times U dot W plus B times V dot W. Okay, and now this brings us to our main goal. And this goal is really kind of a classic idea in mathematics where you take kind of a very simple example of some sort of construction, like in this case, the dot product, and then you prove some things about that object. So we've proven, or we haven't proven, but these are pretty easy to prove, these characteristics of the dot product. And then you look at this and say, well, let's define a new thing that has these properties and then look for some more examples. And that's exactly what we're going to do. So we're going to generalize this idea of a dot product to an abstract vector space. Okay, so let's see how we can do that. Okay, so there we've got it. So notice we didn't really do very much. We just changed theorem to definition, and then we said that V was an abstract vector space over R, so it's no longer Rn. It may in fact be infinite dimensional. And then we need to define something in place of the dot product. And so we'll call that the inner product on V. and we'll denote it as follows. So it has these angle brackets and it has two inputs. So you put a vector from v here and a vector from v here, and the output is a real number. And then like I said, we say it's an inner product if it satisfies these three properties that the dot product happened to satisfy. And this fully defines this notion of an inner product. So notice we have the inner product of v with itself is bigger than or equal to 0, and we get 0 if and only if v is the 0 vector. And then the inner product of v and w is the same thing as the inner product of w and v. So we've got a symmetric inner product here. And then finally, we've got this distributive rule along with scalars. So that's kind of in line with what we had before as well. Now, I'd like to point out one other thing that's common to do, and that is to take this type of definition and weaken parts of it. And if we weaken parts of this definition, we get something called a bilinear form. And depending on how much we weaken it, it might be a certain type of bilinear form, like an indefinite bilinear form, a negative definite bilinear form, a symmetric bilinear form, so on and so forth. So we won't look through all of those types of examples. Okay, so let's look at an example of an inner product on some other vector spaces other than Rn. Obviously, you've got a really nice inner product in Rn, which is just the dot product, which is how we came up with this definition in the first place. Okay, so for our first example, let's say V is the space of integrable functions on some interval which I'll call I, which is a to b. Great. And then, well, notice if we're taking an element from v, then it's going to be an integrable function. So we'll use letters like f and g to denote integrable functions. So we need to define what it is to take the inner product of two integrable functions. And we'll define it like this. So it'll be the integral from a to b of f of x times g of x times w of x. So notice our input is just f and g, but this w of x is always kind of there alongside f and g. So what is w? Well, w is called a weight function. And depending on exactly how you want to define your inner product, you might have different weight functions. Okay, so let's look at some sub-examples of this. So let's maybe say we have v is equal to just polynomials with coefficients in R. So like I said, these are just polynomials. So this is an infinite dimensional vector space. And then furthermore, let's say that our interval is just the unit interval 0 to 1, and let's say our weight function is just the function that's the constant 1. So this is maybe the most basic example. Okay, so now from here, let's find the inner product of x squared plus 3 with 2x minus 1. So notice that's most definitely a polynomial. That's most definitely a polynomial. So we can find their inner product. This will be the integral from 0 to 1 of x squared plus 3 times 2x minus 1 dx. Now we can just multiply that out. That's not too bad. So let's see, we'll get 2x cubed. And then let's see, we'll have 3x, or actually we'll have minus x squared next, and then plus 6x, and then minus 3 dx. But now that's a fairly routine integral to take. We can take all of these antiderivatives. Here we'll get a half because it gets to 2 over 4 evaluated at 1. So here we'll have a half. This will be minus a third. This will be plus 3. And then this one will be minus 3. So in the end, we get a half minus a third, which is 1/6. So that's the inner product of those two. Okay, so let's build another example off of this. And let's say we want to find a polynomial which is perpendicular or orthogonal to a given polynomial. So let's find a polynomial orthogonal to, let's call this polynomial p of x, which is equal to 4 minus 6x. Great, so let's do a little bit of separation right there. So a priori, this polynomial could have arbitrary degree, but we're going to assume that it's linear, which after working through a couple of steps with an arbitrary degree, you'll see that it kind of has to be linear. So let's maybe look at the inner product of p of x, so that's 4 minus 6x, with an arbitrary linear polynomial, which would be like a plus bx. So that's going to be our integral from 0 to 1 of 4 minus 6x times a plus bx dx. So now we can multiply that out, and we'll get that this is the integral from 0 to 1 of, let's see what we have, 4a, so that'll be our constant term. And then what's our x term? We'll have minus 6 times a, and then we'll have 4 times b. So maybe we'll write that as 4 times b minus 6 times ax, and then we'll have minus 6b squared, bx squared, I should say. That's our x squared term. Then integrating that and setting it equal to 0. We want it to be equal to 0 because we want it to be orthogonal. Now, orthogonal means that the inner product would be equal to 0. I guess I didn't define that, but that's kind of an obvious way to define orthogonal based off the fact that inner product is a generalization of the dot product. So let's see. This is going to give us 4a, and then let's see, plus 2b minus 3a. That's what we'll get for this. And then finally, minus 2b. So that's equal to 0. So that's what we get from all of those. Notice I carefully chose this 4 and 6 so that when we took the antiderivative, we would only get whole numbers here. Okay, but we can do some simplification here. 4a minus 3a is a, and 2b minus 2b is 0. So that tells us that a must be equal to 0, but b is free. But if b is free, we could take it to be anything, which makes sense because there should be infinitely many vectors that are perpendicular or orthogonal to 4 minus 6x, just given the fact that you can take any scalar multiple. So let's maybe take b to be equal to 1, and notice that the polynomial, which I'll call q of x, which is equal to x, is orthogonal to 4 minus 6x. Okay, so let's get rid of this and we'll look at a flow chart of a bunch of examples of inner products based off of polynomial vector spaces. Okay, so here's a nice flow chart of examples of lots of different types of orthogonal polynomials, or families of polynomials that are all perpendicular to each other. So recall, in order to define an inner product on a function space, which a polynomial space is a type of function space, you need a weight function as well as an interval. So that's what we've got here. We start off with just the vector space of polynomials, and then we work it through each of these inner products defined by an interval and a weight function. And then we apply something called the Gram-Schmidt procedure, which is a procedure for finding orthonormal vectors based on an inner product. And each of these doubles of an interval and a weight function give us a different family of polynomials. Okay, so let's say you start with the interval -1 to 1 and just the weight function, which is the constant 1. So going through the Gram-Schmidt procedure gives us you something called the Legendre polynomials. And maybe while I'm doing this, editor Noah will put the first few of each of these families of polynomials on the screen. And then next, if you start with polynomials and you have the interval -1 to 1 and the weight function 1 over the square root of 1 minus x squared, go through the Gram-Schmidt procedure, you come up with something called the Chebyshev polynomials. Next, if you've got the interval 0 to infinity and the weight function is e to the minus x, going through the Gram-Schmidt procedure, you get something called the Laguerre polynomials. And then finally for our flowchart, there will be more examples of all of this type of stuff. In fact, you could construct your own example if you wanted to. You could name it after yourself. You could take the interval from -infinity to infinity, and then w of x is e to the minus x squared over 2. Go through the Gram-Schmidt procedure, and you get something called the Hermite polynomials. Okay, so now that we've got this kind of idea of lots of different families of perpendicular or orthogonal polynomials built off of this notion of an inner product, which is a generalization of the dot product, let's quickly look at two more examples of inner products on other familiar vector spaces. So here are two more examples. So the first vector space is the span of all of these trigonometric functions. So it's sine nx, where n is a natural number. So you've got like sine x, and then sine 2x, and then sine 3x, and then sine 4x, so on and so forth. So this is motivated by Fourier series. And then we'll have our weight function, w of x, be the constant function 1 over pi, and then our interval will be negative pi to pi. So for this case, I'll just give you an example of two of these functions being orthonormal. In fact, this is an orthonormal basis for this space already. And we can see that by taking the inner product of sine mx with sine nx. Let's recall that this is a function space, so it has the same type of inner product that we were working with on the last board. So this is going to be 1 over pi times the integral from minus pi to pi of sine of mx and then sine of n times x dx. So something like that. But now taking the antiderivative of that is a little bit tricky. It involves a certain trigonometric identity. So I'll just write the trigonometric identity and let you guys kind of take it from there. So the trig identity is equal to this being equal to 1/2. And then we have cosine m minus n times x. And then minus cosine of m plus n times x. Okay, so let's notice if we integrate this cosine m plus n times x from 0 to pi, we'll just get the number 0. And that is because we'll get sine m plus nx. You evaluate those at pi, and minus pi, you'll get 0. But here, you'll also get 0 unless m is equal to n. And if m is equal to n, then this thing right here is just the number 1. So that's if m is equal to n. But then if you get the number 1 and you integrate it from negative pi to pi, that is an interval of length 2 pi, you get 2 pi times this half out front times this 1 over pi, so you'll get 1. So in the end, you'll get 1 if m is equal to n and 0 if m is not equal to n, meaning that these vectors are orthonormal. Remember, orthonormal means orthogonal, and then they're all unit vectors. So they all have inner product of 1. Okay, nice. So let's look at one more example, and that is something called the Frobenius inner product for the vector space of matrices. So let's recall that m by n matrices with entries in a field, we'll use R, forms a m times n dimensional vector space. Then you can define an inner product as follows. So this is the inner product of a matrix A with a matrix B is the trace of A transpose times B. So just because of size constraints, we can't always multiply A with B because they come from the same matrix vector space. But if you take the transpose, you can. Okay, so this is maybe really cool looking, but it's not quite as interesting as it might seem, as it's essentially just the dot product defined on matrices and then written in matrix notation. Okay, so anyway, let's do an example. So let's find the inner product of the matrix 1, negative 3, 2, 0, 1, 0. So let's say that one. And then the matrix 0, 1, 3, and then maybe we'll say 1, 2, 0. So something like that. Okay, so that means we need to find the trace of this transpose times this. So let's see, the transpose of this, instead of being a 2 by 3 matrix, will be a 3 by 2 matrix. It'll be 1, negative 3, 2, and then 0, 1, 0, and then times just this matrix by itself, 0, 1, 3, 1, 2, 0. So we need to find the trace of that. Let's recall that the trace is just the sum of the diagonal elements. Okay, so now let's multiply these two matrices. So let's see, we've got a 3 by 2 times a 2 by 3. That means we should end up with a 3 by 3. So if we take this product right here, so swivel this first row into this first column, we get 0. So that'll be this entry. And then swivel this into this and we'll get a 1. And then finally a 3 here. I'm doing more work than I need to do because really I only need the diagonals, but we might as well find the full product. And then for swiveling this into this, we get 1. And then this into this, we'll have negative 3 plus 2, which is negative 1. And then this into this will give us negative 9. And then finally here we'll have another 0. Here we'll have 2, and here we'll have 6. So from that product. So like I said before, the trace is just the sum of the diagonal elements. 0 plus negative 1 plus 6 is 5. So that's our trace of, or that's the inner product of these two matrices. So now let's maybe leave you with a homework and let's find a matrix orthogonal to the following 2 by 2 matrix. And this is going to be a matrix orthogonal in the sense of this inner product, which is, like I said, called the Frobenius inner product. So let's say we've got our matrix A, which is 1, 3, 0, 2. So maybe post in the comments what you get for the matrix or maybe the family of matrices that's orthogonal to this matrix. And that's a good place to stop.